Can you guys all hear me okay? Excellent. I trust you all found things to do last night. Cool. Yeah, I know we're kind of cool down. So, thank you for joining us on the last day of what's been a really wonderful conference. This morning we will have two speakers, Drs. Kimberly Budil and Sarah Beach. So Dr. Kim Budil began her career at Lawrence Livermore National Laboratory as an applied science graduate student studying at the University of California, Davis. She has held multiple positions across the Livermore lab, working in a variety of different departments, including physical and life sciences and the National Ignition Facility. Currently, as the Vice President for Laboratory Management at the University of California, she is responsible for the university's management oversight of several of the University of California's laboratories. Dr. Budil has served on the American Physical Society Committee on the status of women in physics and participated in 2 international conferences on the women in physics. So without further ado, I'd like to introduce you Dr. Budil.
Can you hear me now? Good. I'm really happy to be here. I appreciate being invited. Thanks very much. I spoke yesterday morning at UC Santa Cruz, and then came here. So on the good news front, I've given this a test run, and my flights all made it, and the weather was nice. On the downside, I may have peaked too soon, so works good. I've had kind of an unusual career path, so hopefully this will introduce you to a different way of thinking about a career in physics. I'm going to spend a little time talking about me and how I got to where I'm at. Then I'm going to talk a little bit about my current job and tell you about national laboratories, because I currently am in a research administration position, so I'm not personally doing research, but I'm providing oversight to the 3 national laboratories that UC is responsible for: Livermore, Lawrence Livermore, Los Alamos, and the Berkeley National Laboratory. And then we'll jump in the way, way back machine. I'll talk to you a little bit about what's happening in the field that I started in today. So about me. So I made 2 very impactful choices early in my academic career that kind of put me on this path. I knew from a very, very young age what I wanted to do with a great deal of certainty. I was going to be a lawyer, completely convinced, from the time I was very young. And all through high school, I took physics and math courses and did very well in them. I enjoyed it a lot, but I was going to be a political science major, go to law school, and then work in the government. And my math teacher in high school was just ridiculously angry at me about this. You have to go to college and do something technical, meet women in technical fields, but I was convinced I was on the right path. But then I got a chance to talk to some lawyers, and they agreed with my high school math teacher. They said you should get a technical degree, because if you do that, when you go into the law, you'll have opportunities you wouldn't have otherwise. For example, you can do patent law, which requires a technical background. So I thought about the science I'd taken in high school. I'd done biology, chemistry, physics, and I thought about which ones I liked best, and I decided that I liked physics best. It was the discipline that allowed me to memorize the fewest things, develop a base of concepts that I could really were intuitive, that I could really understand, and then build those into understanding, very fundamental understanding of a whole range of things, which I really enjoyed. It was very math intensive, which I liked. So I thought, great, I will major in physics. So just like that, between the time I applied to college and the time I started, I moved from political science to physics. And partially because of that change, I changed where I was going to school. I ended up at the University of Illinois at Chicago. Most people know Urbana-Champaign, the Fighting Illini. UIC is home to the mighty Flames, the University of Illinois. This campus actually has history in my family. It started on Navy Pier after World War II in Chicago to accommodate returning servicemen. And my dad was an electrician on the pier. He was a returning serviceman. My mom worked at the university, so my family started at this campus. They eventually formed a permanent campus, and the year before I started, they changed the name to UIC. It used to be University of Illinois Chicago Circle, because of this traffic interchange. So it's the only university in America named after a traffic interchange. When I was there, we called it Harvard on Halsted. And I joined the physics department, and this was a really impactful decision for several reasons. One, one was the change of major, but the other was I got a job in the physics department. First as a secretary, which taught me about all the things I really didn't want to do in life. I didn't want to be a support person to a group of physicists. But I got introduced to a whole crew of physicists, and they said, why don't you come and work in our laboratory? So this was the first experience I'd ever had of doing research. The professor I worked for, Charles Rhodes, was actually a very big name in science, still is. He was one of the fathers of the Excimer laser. He had, for a university program, an extraordinarily large research group, and had built an enormous laser system and had brought in researchers from around the world. They were leading the field in laser matter interactions, basically looking at what happens when you put one atom in a very strong laser field. I went into the laboratory, I got to build a laser, I got to write a paper, I got to have real experience with this incredible group of researchers, and all thoughts of law school went away. I've now found my calling. It was the hardest, most challenging thing I'd ever done, but also the most rewarding. So I was now on a career path to go to graduate school in physics, and a second opportunity came my way. Professor Rhodes had a group of researchers who would visit during the summers from the two national laboratories, Lawrence Livermore and Los Alamos. And through them, I found out about a summer research opportunity at Livermore, which I applied to, so I could get an opportunity to see what another laboratory environment was like. I didn't get accepted. So I continued through my senior year, and toward the end, as I was thinking about graduate schools, I got a letter from the folks in Livermore who said, well, the summer program was small, we didn't really have space, but if you're interested in graduate school, we have a great program, we'd like you to come. So that's how I ended up in California. They flew me from Chicago to California, so this is Northern California, but still California, in February. Took me to Lawrence Livermore, which is about 45 miles east of San Francisco. The campus is 1 mile square. And in February and March, it looks like this, lush and verdant and green. California, it rains in the winter, it's warm, doesn't snow. And that was pretty much all I needed to know at that point in time. And the University of California, Davis had a little outpost on the eastern border of the site in this one building, Hertz Hall, where they had a resident faculty in this Department of Applied Science that had been actually founded by Edward Teller in the early several decades ago. So I came to Hertz Hall, did all my coursework with this resident faculty, a few courses done televised from UC Davis, but I spent my time on this site, not the Davis campus. I had to visit Davis to defend my dissertation, to meet with my dissertation committee, and to file my thesis, but that was really it. And I did my research at Lawrence Livermore, and I got another very life-changing experience. National laboratories, as opposed to university departments. I've worked in, as I said, a very well-funded, large-scale university research department, and I could not believe what I experienced when I walked into the labs at Livermore. Just the scale at which people work, the collaborative environment, just the amount of stuff. I mean, as an experimental scientist, it was really quite extraordinary. So again, I stuck. I did my thesis research there in what would now be called high energy density science, and then joined a research group there as a postdoc. And I learned the last lesson that I'd like to impart to you, which is when I was looking for a postdoc, part of finishing graduate school is becoming the world's foremost expert in a very, very specific problem space. And I'm very much not the kind of person who wants to do one problem in a very specific, narrow space for the rest of my career. So I was looking around for opportunities for a postdoc, and I found a job ad for a postdoc at the laboratory in another distant division with people I didn't know, to do work I didn't honestly understand. It had terminology in the description of the physics that I'd never heard. I went and talked to some of my colleagues to try to figure it out. But it said things I did know. Talked about X-ray diagnostics and laser systems and experimental physics. And I thought, well, I know how to do that. I can learn the other part. And fortunately, that group agreed with me. I moved from this very small tabletop laser laboratory experience to what was at the time the world's largest laser facility, NOVA, and started on the path that would take me to where I am today. Now, where I am today is kind of interesting. I had did laser experiments for about 10 years at Livermore. When NOVA was shut down, so that the laboratory could start building the National Ignition Facility there, I switched to computational physics and did computational research for about 4 years. And then I got interested in material science. I got an opportunity to go to Washington, D.C. I worked at Department of Energy for 2 years as a science advisor. And that really moved me from being a researcher to being a research leader and manager. As I realized while I enjoyed research and I was good at it, I was a really great program manager, and I could enable lots and lots and lots of researchers to do amazing things. So pretty much from that point on, I've been in a management position of one kind or another. I've managed everything from condensed matter physics to plasma physics to development of computational models for high explosives and metals. So pretty much every field you can imagine. I characterize my technical depth across that space as mile wide, quarter of an inch deep. But really fascinating, and I've gotten to work with an enormous range of really bright, enthusiastic, creative researchers, help them shape their technical agenda, secure resources to do their work, and then really see that work have an impact. The key thing that differentiates national labs from universities is that while basic research goes on in that environment, the goal really is to apply it to big problems. National labs have a huge range of disciplines represented, and they were founded to solve big problems in the national interest. And they're different from industry because they're allowed to work on problems for very long time scales. So there's no product cycle driving how fast you have to turn this out. The urgency really comes from the nature of the problem you're trying to solve. So that's what brought me where I am today. Last May 1st, I joined University of California Office of the President. So UC is a very big system. There are 10 campuses, 5 medical centers, and 3 national labs as part of the system. The Office of the President is the system-wide synchronization hub. Anyone who's familiar with universities knows that no one really tells the campuses what to do. But my job in that team is to help ensure that the 3 laboratories that we're responsible for are successful, particularly in their science and technology work, which is really fun. So as I said, I'm responsible for Lawrence Berkeley National Lab. The Berkeley Lab sits on the hill above the UC Berkeley campus. So it's a kind of interesting and unique university national lab hybrid. Huge numbers of students and postdocs work up, and faculty members work up on the hill in the laboratory and move seamlessly back and forth. My old laboratory, Lawrence Livermore National Lab, that's kind of the best part, used to work there, now they all work for me. Lawrence Livermore is a national security lab. It's a little bit bigger. Berkeley has maybe 3,000–4,000 people total. Livermore is about 6,000 people. And Los Alamos National Laboratory, which is in northern New Mexico, about 45 minutes north of Santa Fe, up on a mesa, a very beautiful part of the Southwest. There's about 10,000 people at Los Alamos National Lab, and it's also a national security laboratory. So I'm going to give you a quick high-level survey of the kinds of research that go on in each of these 3 places. These 3 labs all grew out of the University of California. Los Alamos was founded during World War II by the folks from UC Berkeley, who went to New Mexico to run the Manhattan Project. They're all still infused with the ethos of E.O. Lawrence. Lawrence really invented big science, where large multidisciplinary teams would build very complex experiments, in his case, and try to do things at a level of complexity and ambition that were very hard for individual university researchers. And that really is how the laboratories work today. They tend to be very large-scale, multidisciplinary science and engineering in the tradition of E.O. Lawrence. Again, the labs do a lot of really innovative engineering, first of a kind, one of a kind, at incredible scale in some cases. They're what are called federally funded research and development centers. This is also a distinguishing characteristic. They're supposed to be science advisors to the government. So as opposed to just trying to get money from the government, the goal for the national laboratories is really to work in partnership with leadership in the country to understand what the most important problems are, and then help provide technical solutions to those problems where applicable. They're supposed to provide a really intense competition of ideas so have a very academic ethos of how the science is pursued. And they're driven by technical excellence and the impact of the work. Again, the goal is to make an impact, and I felt good every day knowing that the research I did meant something at a scale that you could notice on the national scene. And the labs really continue in this vein. The way they're managed by UC is slightly different than it used to be, but the first order, the laboratories still maintain these characteristics. So this includes things that go on at all three laboratories. The national security labs have a large nuclear security component to their work, and have had work in both nuclear deterrence, but also non-proliferation, counterterrorism, and assessment of nuclear threats almost since their inception. So a lot of work from lab researchers going around the world trying to secure vulnerable nuclear materials and developing tools and technologies to help that enterprise. Large and growing programs in energy. This is particularly a focus for the Berkeley Laboratory. Developing advanced biofuels, working on materials for energy technologies. At Livermore in particular, fusion research has long been a centerpiece. That's home of the National Ignition Facility, which is pictured here. Currently the world's largest, most energetic laser. The labs have also worked in health and environment since their inception. In the early days, it was about understanding the effect of radiation on human health. Today, it's extended in many, many directions. The application of high-performance computing to biology. You'll remember the Human Genome Project was a Department of Energy initiative, which seems a little strange. Department of Energy is not full of biologists, it's full of physical scientists. And I think it's important to remember that that revolution was founded on science and technology base that the physical sciences brought along. So that partnership between the human health community and the physicists was really important. Today it's computing that's revolutionizing this. This is a simulation trying to understand disease spread so that you can do better public health mitigation and management of outbreaks. And then tools and technologies for detection. Again, a lot of the work that could be done for trying to understand the security aspects, someone trying to engineer a virus, for example, are directly applicable to standard public health practices around the world. So the labs have developed, for example, rapid technologies that allow you in several minutes to identify the nature of a pathogen. And then climate change prediction. The labs really invented large-scale simulation. Starting again, they were using computers during World War II. And it was very clear relatively quickly that the same kinds of large-scale multiphysics simulations that were being used in the national security environment would be very useful for trying to understand a very complex multiphysics problem like the climate and how it would evolve over time. They work in a very particular way in this sort of integrated, interdisciplinary manner, taking basic and applied science. Again, fair measure of basic research goes on at the laboratories. A lot of leading researchers. Berkeley Lab is home to a number of Nobel laureates, for example. Even Livermore spawned one Nobel laureate. But the real focus is on taking that scientific knowledge and applying it to big problems, coupling it with this very unique base of engineering R&D and skill, and utilizing high-performance computing as a sort of a closed cycle, very close couple, to solve enormously complex problems. And HPC was another field that was really revolutionized by the national laboratories over the last decade and a half. The laboratories working in partnership with industry were able to help the industry develop an approach and an architecture to large-scale simulation that led to the deployment, pretty routine deployment now, of very large-scale computers. So I was looking this up earlier. If you look at the chips in an iPad or an Apple Macintosh, there are a few hundred gigaflops. So a teraflop is 1,000 times a gigaflop. So a teraflop chip would be about 5 to 10 times bigger. Petaflop's 1,000 times bigger than that. So the way these computers were really, these speeds were really achieved for these computers was by ganging together effectively large numbers of chips. So massively parallel computing is really the order of the day today. The biggest problem is if you just keep, I mean, you know how hot your computer gets if you just sit it on your lap. If you gang together lots and lots and lots and lots of chips, it gets very hot. You dissipate a huge amount of energy. These machines take a huge amount of energy to run. If you go another factor of 1,000, which is where we're aiming to exaflop computing, you'd need a nuclear power plant attached to your computer center. So the big challenge today is learning how to change the architectures and the chips very fundamentally so that they use very, very, very little power per chip. And that work is ongoing today. There's a big exascale computing initiative from DOE that again works with the industrial chip and computer manufacturers and the laboratories and the simulation experts in close collaboration to develop chips that can have the right performance characteristics, but can also work the kind of problems that we care about. Not just, you always read the top 100 list for the computers, running LinPack, which is a very simple little routine that's designed to make your computer go as fast as possible. These computers have to do real problems, and that's a lot harder problem. Okay, so I'll give you one little vignette from each of the 3 laboratories. This is an example of work that was done at Lawrence Livermore, trying to improve the aerodynamics of trucks on the road. If you think about how many trucks are on the road, how many miles they drive, how much diesel fuel they use, very small improvements in the efficiency with which those trucks can travel will have enormous impacts on the amount of fuel they need to use. So the goal here was to use modeling and simulation to design a more aerodynamic truck that could improve its fuel efficiency on the order of, say, 10%. So the researchers at Livermore did a huge number of simulations, large-scale simulation studies, and then finally, at the end of that process, went to a full-scale wind tunnel test to validate what they were doing. And were able to develop approaches that allowed the reduction of vehicle drag by of order 10%, which is a huge impact in that sector. At Los Alamos, as I said, nuclear security has been a core component of those laboratories since their inception. They have very large programs developing tools and technologies to support organizations like the International Atomic Energy Agency. So IAEA has a responsibility to go out and monitor the deployment of nuclear power around the world, which nuclear power is being deployed at a pretty vigorous rate around the world, not in the US, but other places. The list of countries that are trying to acquire nuclear reactors, in many cases, are the list of countries that you would probably not want to have large stocks of nuclear materials. So the IAEA function is very important, ensuring that everyone adheres to international norms. So the laboratories develop technologies, detectors that inspectors can use as they go through plants, and place detectors that can monitor the activity in a nuclear power plant, for example, over long periods of time. And then the inspectors from IAEA go to Los Alamos and are trained there in how to use that equipment, how to do that function. Berkeley Labs' centerpiece is biology for energy and environment. And they have very large-scale programs on trying to develop low-carbon fuels from biomass. If you think about biofuels today, ethanol from corn, you're utilizing food crops. It's very energy intensive to produce food crops. And it has unintended implications. So if you divert a large part of the corn that's produced to developing fuel, there are people in the world who are dependent on that crop for food, so it raises food prices. So it has unintended feedback cycles. So what Berkeley would like to do is be able to use non-food crops, sort of the waste crops that would not be able to be eaten or used beneficially, and break these down and turn them into fuels. Turns out it's very hard to break these types of crops down. This is switchgrass, to break down the cellulose in them. So they're developing all sorts of techniques like, for example, using bacteria to ingest these grasses and then digest them and convert them into a more useful form. So something that can be a process that's not energy intensive, that can be scaled up to a size that's big enough that you can make enough fuel that someone might care about. In health and the environment, a lot of work going on. This example shows the climate research from the 3 laboratories. Berkeley has a very extensive climate science program, really trying to understand the feedback between the level of carbon in the atmosphere and the evolution of the climate over time. Los Alamos really has the core expertise on the oceans and ocean circulation. If you think about how much water covers the earth, one of the largest driving terms in how the climate evolves is what's happening between the ocean and the atmosphere. It's a very, very hard problem. So they're working hard at that, trying to understand that feedback cycle. And then Livermore hosts an interesting program called the Program for Climate Model Diagnosis and Intercomparison, or PCMDI. This is the repository for all of the climate models around the world. So all the data and the models are hosted at Livermore. And when you read the reports of the Intergovernmental Panel on Climate Change, and they show comparisons of models, this is the program that does that work and acts as the sort of unbiased center where those projections are produced and vetted, put out. There are folks also doing research on different terms in this, trying to understand how to differentiate human impacts from naturally occurring impacts. For example, they did research on the impact of volcanic eruptions on temperature, global temperatures, because volcanic eruptions put a lot of particulate matter up into the atmosphere, which tend to drive this climate cycle, global temperature cycle, much like carbon would. In international and domestic security, the landscape's changing a lot because the world's changing very quickly. We do traditional work on materials. This is a good example of one of those grand challenge problems. If you've ever been to a port and you've seen some of the large cargo ships that come into a port, they have thousands and thousands and thousands of cargo containers on them. One of the goals that the Congress set was to do 100% screening of all those cargo containers. It's almost impossible just because of the sheer number. But the other requirement you have to hit is that they have to move fast, because every second that cargo container spends sitting on the shore is time that's not, the contents are not being productively taken to market. So there's a commercial aspect to it, there's a technical aspect to it. How do you scan these cargo containers and find out if there's something that you don't want in there? You have to be cognizant of the fact that sometimes cargo containers contain things like people who are being smuggled into the country, so you don't want to do anything that might be too harmful in case there are people who are in the cargo container. And you also don't want to generate a lot of false alarms. So if you're the inspector at the port, your portal goes off every 4 seconds. What do? You turn it off, because you just can't stop the flow of commerce. You can't possibly deal with the false alarms, and you know that most of them must be, so you play the odds and you just let them go. So labs have been developing both technologies to scan containers, but also practical ways to deploy them so that you can reduce the number of false alarms and keep the pace of commerce going pretty quickly. For example, by using smart algorithms. There are a lot of radioactive things in the environment that are naturally occurring, so you want to be able to differentiate the big truck of kitty litter from, someone trying to smuggle nuclear material into the country. Cyber is a huge focus area for a lot of reasons. Cybersecurity, just securing networks. The labs have pioneered a lot of techniques to do network mapping, so you can really understand the nature of your network, which most places do not very well. But also looking at emerging areas. The grid is one of the biggest cyber systems in the country. The US grid does not have any kind of national blueprint or operating model or governing board. It's a whole bunch of little local grids. They all present vulnerabilities, and they all have varying degrees of sophistication in how their control systems operate and protect themselves. But you also have to worry about those cyber systems being able to manage the grid. So you've seen over the last decade, there have been a number of very large-scale blackouts because it's very hard to, when something goes wrong on the grid, to control how that cascades. So the labs are working on things like, how do you integrate variable sources of power? If you put a lot of solar energy on the grid, that doesn't come as nice. Even baseload power, it comes in a very intermittent fashion. The grid has to be able to manage that, and these computational systems are helping folks understand how the grid operates to make that process better and more efficient. Okay, so now we're going to go back to where I started. I said I was I did strong field laser matter interactions. I moved on to this large laser facility where I did what's now called high energy density science. And if I woke up tomorrow and you told me I'd have to go back and do research, this is where I'd be. I'd be at the National Ignition Facility at Livermore, currently the world's largest, most energetic laser. It has 3 major components to its mission space. It was designed as a facility that could produce the conditions for fusion ignition. So fusion of deuterium and tritium, which is only found in a few places in the universe, so in the sun and in stars, for example, but also in nuclear weapons. So at the end of nuclear testing, that experimental platform was taken away, and these laser facilities became a big focus of trying to understand matter in these very exotic states. Turns out it's a really interesting frontier science platform because the same conditions are found in other parts of the universe in similar conditions. Very high temperatures, very high density objects are found throughout the universe, and our ability to understand them is limited by our ability to understand the properties of the components. So it's very hard to do experiments to understand what the center of giant planets look like if you don't have an experimental system that can get you there. And then the ultimate goal, and the one that keeps many people coming to work every day, is the prospect for fusion energy. So if you can really make this process work and demonstrate fusion ignition in the laboratory, where you get more energy out of the end than you put in starting as a wall plug, you could conceivably turn that into a power plant. And fusion energy has a lot of nice attributes. It's the other nuclear power, the clean nuclear power where you don't end up with lots of radioactive waste and chemical disposition. So that's what NIF is about. This building is very large. You can fit 3 soccer fields on top of the building. At its tallest point, it's 7 stories tall. So just to give you a sense of the scale. That's one laser system, fills the entire building. This is a shot of the target bay area. So this is a 20-meter diameter sphere. These are the beam lines coming in, these boxes here. Each one of these boxes contains 4 beam lines, so that each beam is about that big square. There are 192 laser beams coming in. NOVA, my old laser, was 10 beams. NOVA was also designed to give fusion ignition, but we learned pretty quickly in that experimental program that it wasn't big enough. So that set the spec for this next laser. The energy produced is a little bigger than this now. They demonstrated over 2 megajoules of total energy, and that's 2 megajoules in the ultraviolet and the blue. The peak power produced is about 523 terawatts, or a little higher, as I said. That's produced in a pulse that's about 20 nanoseconds long, so 20 billionths of a second long. So if you consider the time scale for that brief instant, that amount of power is about 1,000 times more than the US power generating capacity in total. Only lasts a short amount of time. Huge building, large number of optical systems, a whole host of new optical technologies had to be invented to build this laser because of the energy that was going to come through it. 60,000 control points, none of which are touched by a person. So there's a computer system that runs the whole thing. This giant building-sized laser has other applications. You may have seen this movie. If you haven't, I encourage you to go see it. It played the part of the warp core in the Enterprise. So that's how you know you're very high tech. J.J. Abrams comes to your lab and tells you. So I encourage you, if you haven't seen it, to go and see it. We had the Star Trek crew on site for a number of months filming. And if you go inside that target chamber, it is not the warp core of the Enterprise, unfortunately. What you find at the very heart of it are these little targets. And this is a standard inertial confinement fusion target. It's a little gold can called a hole room. Hole room is German for hot room. This is about 1 centimeter long and say 0.5 centimeter in diameter. So again, I'm taking this giant laser, I'm taking 192 of the beams that are about this size. I'm focusing all that energy down, 96 beams into one side, 96 beams into the other side. Those laser beams array themselves around this gold can and get absorbed by the walls. The walls heat up and then they re-radiate all that energy back out as X-rays. But instead of radiating out just these discrete spots, the X-ray bath is very uniform now. So you have a very hot, uniform bath of X-rays. And in the center of it, you place this little capsule, typically made out of plastic, although they can be made out of other materials. One of the promising new materials for capsules is nanocrystalline diamond. if you hear a talk from someone from Livermore, they will call it high-density carbon. There's a lot of sensitivity to saying I'm gonna take diamond capsules and put them in gold rooms if you're getting your funding from the government, so these are, the standard capsule today is made out of plastic, and it's a hollow shell, and in the center of it is deuterium and tritium gas, and then a solid layer on the inside, a solid layer of deuterium and tritium on the inside of that plastic shell. So this X-ray bath heats up the capsule, the outer surface blows off, and then the rocket effect causes the capsule to start moving inward. And the whole trick for fusion is to get that capsule to move in fast enough so that you can confine the fuel at a very high density and get it to start fusing. So in the fusion process, a deuterium and a tritium heavy hydrogen come together. If they fuse, they release an alpha particle and a neutron, and you get about 450 times more energy out than you put into making the reaction go. It's very hard to get atoms to fuse together. That's why it happens in places like the sun, where that gravitational force is extremely large. So you need this to come together and bring that fuel to a very high density before the capsule starts to come apart. And there's two things that work against you. One is that all the little perturbations on the capsule surface, any non-uniformities in that X-ray bath, make the capsule become not spherical. So any asymmetries or instabilities on the surface will tend to work against you. They either put cold material in the hot center where you're trying to get the fusion to go, or they break the shell up, and then the whole thing comes apart before the fusion has a chance to take off. The other thing that works against you is that it's a hydrodynamic implosion, so the shell will come in, and eventually it will rebound. It'll have the smallest radius, and then it'll start coming apart. So if you don't get this process to go before the capsule starts to rebound, again, the temperature will drop and the fusions will stop. Both of those things are very hard. So where are we at with this? And this process, this proposal to do fusion by this mechanism was conceived within months of the invention of the laser. That's a long time ago now. So we've been working at this forever. The traditional statement about fusion is that it's 50 years from whatever day you ask. It's no longer 50 years away. I think we're getting very close. But it turns out that although it sounds simple, actually controlling the shape of that capsule and really getting the velocity high enough without the shell breaking up is a very, very hard problem. And nature has not been as cooperative as we would have hoped. But, so this plot, this is a snapshot from a paper that's in Nature, written by the team at Livermore, showing their most exciting accomplishment yet. So this shows yield from the capsule in kilojoules as a function of laser shot number. So this is just a whole bunch of experiments and the amount of fusion energy that came out. And I told you get 2 megajoules from the laser. You lose roughly a factor of 10 every time you do one of these conversion steps. So you bring in 2 megajoules and you lose 10%, you get about 10% of that energy out in X-rays, so now you're down to 200 kilojoules. The X-rays heat up the capsule, but you only get about 10% of that energy actually into the capsule, you get about 20 kilojoules. So you need to get, in order for you to have the first step, which would be fuel gain, more energy out of the fuel than you put into the capsule, you need to get of order 20 kilojoules or so. So that's what the Livermore scientists were able to demonstrate recently. They changed the shape of the laser pulse. This was their original point design. It wasn't working very well. They were stubbornly stuck down here about 4 kilojoules out. They changed the shape of the laser pulse from what they call low foot design to a high foot design, where you push a little harder initially on the capsule. If you push too hard in the beginning, the fuel will get hot, and it's harder to compress a hot fluid than a cold fluid. But it turns out if you don't push hard enough, you don't get enough velocity to get the thing to come together. So they changed the shape of the pulse so they could push a little harder, and they were able to achieve what's called fuel gain. So they generated more energy out of the fuel than they put in. And they did that in 2 ways. One is that the fusion reactions produce a certain number of fuel. But when I showed you that diagram, I said there are alpha particles produced. those alpha particles can interact in this very dense plasma with other stuff and generate more and deposit heat, and again, bootstrap this process, generate more energy out. So this red bar shows the amount of yield that was added by this self-heating process from the alpha particles being trapped. That's a big deal. It's only a first step, but remember, factor of 10, factor of 10, factor of 10. Instead of 50 years, maybe we're talking about 5 years. So it's starting to get really exciting there. And the team is working on a whole host of things, as I said, different capsule materials, nanocrystalline diamond, different laser point shapes, different whole room designs to make it more efficient. So there are a whole host of variables to work on here, and it's hopefully moving in a really great direction. Something a little closer to what the kind of work I did. As I said, I'm a simple person. I didn't do capsule experiments because those are 3D. I did planar experiments because you can do 1D physics. And I was worried about understanding the property of materials under shockwave conditions. I looked at, in particular, the growth of ripples when you pass a shockwave over them. But I also did work like this where we're trying to understand the compressibility of matter. So the equation of state of material. This is another piece of research from Livermore where they're trying to get materials that you might find in the center of giant planets to pressures that are representative of the center of giant planets. So that would be hundreds of megabars to gigabars. So this was a result they had at 50 megabars. They've since gone considerably higher than this. In carbon, you put a little flat piece of this nanocrystalline diamond on the side of your whole room, so right here, and it has steps in it. Use the same X-ray bath, heat up the surface, which causes material to come off and launches a shock, and then the shock breaks out to the back surface. And the surface is stepped so that you can measure the difference in the breakup time between the different thicknesses. And you can use that to derive then how the material compressed up and what the velocity of the shock was in the matter. When that data was analyzed, they were able to measure the stress induced in the material, and the compression resulted up to about 50 megabars. And prior data had only gotten you up to about 10 megabars. Most of the really high quality data is down here below 10 megabars. So very extraordinary. They've gone about 100 megabars now, and this data is coming fast and furious. So really exciting for the planetary science and the astrophysics community to have real data platforms, terrestrial data platforms, to build understanding that you can put into computer models that will really help us understand these extreme objects in the universe. And with that, I would be glad to take any questions.
I was wondering if the laboratories are more for postdocs or like graduate work or a combination?
Both. The labs all have very large summer student programs and year-round student programs. The program that I came through no longer exists, but there are huge numbers of students doing their dissertation research at the laboratories as well. The summer programs are a lot of fun because they have a lot of activities so that you can learn about all the different kinds of things going on at the laboratory, lectures and social opportunities to meet folks. But undergraduates, graduates, and postdocs, all in residence.
How exactly do you change branches? Like, say you wanted to switch from like energy to health environment, like how would you go through that? And do the national labs provide like some type of training and education? Because I know almost nothing about biology, but if I wanted to work in something that's biology related, I would want to like know more.
Right. So the first thing is you have to think a little bit about what your toolkit looks like, right? So if you're studying physics, you know how to solve problems, and you have a set of tools that you know how to use. You either know how to use computers and write simulation codes, or you know how to do experiments, and you have a set of detectors or particular types of experimental science you're good at. So I would think through what your toolkit is and how you can use that in other ways. The second part is you have access to experts in other fields. So you go and talk to people, and you read, and you go to lectures, and you try to understand what the interesting problems are. And again, I know what my toolkit is, and I know what the problem is. Is there a way that I can see this through? And then the neat thing about the labs is that because these teams are large, it's a little bit easier to get an opportunity to move into a project in a more junior role and really learn something new. You know, bring something to the team. You're not going to be the lead researcher when you switch fields. So as I said, I did this several times, and it really was a process of, an iterative process where I was working on something, I got interested in a problem that was sort of a branch off of that. I went and built relationships with folks working in that area and they helped me understand what the problems were. And then I slowly built up my knowledge base and started working in that area. And then we would propose joint projects